Today we start divergence of a vector field. Now, what is a vector field? Every point in the space is completely assigned by a vector quantity. That space we call a vector field. For example, flow of fluid. Here the divergence of vector field which measure how much flow of fluid is expanding or contracting at a given point in the region of vector field. Now firstly we define the divergence of a vector field. For that we consider V is a vector point function and that function is a continuous differentiable. Such a vector term is a function of x, y, z. That is, the vector v is defined as unit vector I v of x plus unit vector j vy plus unit vector k vz. And del operator that we defined earlier, it is unit vector I dab of dab x plus unit vector j dab of dab y plus unit vector k dab of dab z. Therefore, the divergence of vector point function is denoted as del dot v or divergence v, and that term we simplify by using the two terms. First bracket we write unit vector I dab of dab x plus unit vector j dab of dab y plus unit vector k dab of dab z into vector v unit vector I vx plus unit vector j vy plus unit vector k vz. The dot product of the two terms we simplify by taking I dot I is 1, j dot j 1, k dot k is 1. Therefore, we get daba vx by daba x plus daba vy by daba y plus daba vz by daba z. That term represent divergence of vector point function and it proved scalar quantity. Hence, divergence of vector point function is a scalar quantity. Now then we see what is the physical significance of divergence of vector point function. The physical significance of divergence of vector point function means vector point divergence of vector point function. It gives the total flux flowing out, or we say diverging, per unit volume of a volume element in vector field region. Hence, divergence of vector point function gives the total flux flowing out or diverging per unit volume of a volume element in vector field region. That term we prove by considering a small volume element we choose small volume element. That volume element we considering a rectangular parallelepiped whose volume is dx, dy, dz. Hence we choose small volume element in vector region. That region we call here at the center. If v is the vector point function, that vector point function we choose vector v, means that vector v has three components, vx, vy and vz. At the point P, v is a vector point function whose components along x, y, z axes are vx, vy, vz, and that in that region we choose a small volume element whose side lengths are dx, dy and dz, means this is x component, y component and z component. Such a small volume element in the region of vector point function, that here the v is a function of x, y, z. Therefore, its component along the three coordinate axes are x, y, z. Now, we are considering the three differentiable functions, means the three components dabba vx by dabba x, dabba vy by dabba y and dabba vz by dabba z. That three terms represent the rate of change of vector components along x, y, z axes respectively. Now we find what is the variation of vector field along the x axis. For that purpose, we are considering the x component of the vector point function, means Vx. We write its magnitude. Now what is the magnitude of vector point function at the center of one of the face? That face we call A, B, C, D and other is E, F, G, H. Now we find the magnitude of the x component of vector point function at the center of the face A, B, C, D, and that is directed into the volume element. Hence, its magnitude we write, it is Vx minus dabba Vx by dabba x, and that magnitude is at the center of the face A, B, C, D. Therefore, we write it is dx divided by 2. Similarly, the magnitude of the x component of the vector field at the center of another face E, F, G, H, that field is normally directed outward and its magnitude is Vx plus. Why we take plus? Since if the flow is flowing outward through the element along positive x direction, we take positive Vx plus dabba Vx by dabba x into dx by 2. Since dx by 2 is the center of the phase. Now, these two components, two terms, the magnitude of the vector point function, if directed normally at the center of the phase ABCD into the volume element, that is Vx minus dVx by Vx by Vx into dx by 2, and other term, the magnitude of the vector point function, it also directed normally outward of the element at the center. Therefore, its magnitude is Vx plus Vx by Vx into dx by d2. Then we find here, if the vector point function V and the normal drawn to the face area of the element, normal drawn to face area of the element, are in the same direction, then the flux of the fluid is taken to be positive. Then we just write here the flux of fluid, or only we write flux is taken to be positive. But if the vector point function and normal drawn to face area are opposite in direction, then in opposite direction flux is taken to be negative. Therefore, how we calculate the flux? The flux of the vector point function through any face of the element is taken as flux flowing through any face of the element, flowing through any face of the element must be equal to the area of the face multiplied by the normal component of the vector point function V. Now here, using that term, we find now what is the flux entering through the face ABCD along the x-axis. Flux entering through the face ABCD is how much? That we write. Firstly, what is the area of the face ABCD? That area is dy dz multiplied by what is the normal component of the vector point function, whose magnitude we know. That magnitude is Vx minus Vx by Vx into dx by 2. Now what is this dy dz? This is the area of the face A, B, C, D. Similarly, we calculate. Now, what is the flux living through the element, or we say the flux flowing out through the element through the phase E, F, G, H, the flux living or out through the phase E, F, G, H is. How we write? The area of the phase E, F, G, H, that area is same dy dz into normal component of the vector point function whose magnitude is Vx plus Vx by del by x into dx by 2. Now we are considering this equation 1 and equation 2. These two equations gives the net flux flowing out. Then we calculate net flux flowing out from the element along x-axis. Now, what is the net flux flowing out from the element along x-axis? That we take the difference of the equation 1 and 2. That term is, we take the common dy dz and the two brackets we simplifying here. Vx, first bracket, Vx minus daba Vx plus daba Vx by daba x dx by 2 minus another bracket Vx minus daba Vx by daba x into dx by 2. We take the common dy dz. Now simplify the bracketed term. Vx minus Vx, it get cancelled. Minus minus it becomes twice daba Vx by daba x dx by 2. But again we did get 2 cancel, and simplified term is daba Vx by daba x into dx, outside is term dy dz. Now this is the equation number 3. If the equation 3 represents the net flux flowing out from the volume element along x-axis, similarly we calculate the net flux flowing out from the element along y-axis is, that term is daba Vy by daba y into volume element is same dx dy dz. Similarly along z-axis, what is the net flux flowing out along z-axis? That term is daba Vz by daba z into dx dy dz. We know the net flux flowing along x-axis, y-axis and z-axis. The three terms are known. Therefore, we calculate the total flux flowing out from the element is, we take the sum of these three terms and common term we take outside, dx dy dz, hence dava vx by dava x plus dava vy by dava y plus dava vz by dava z. Outside we write dx dy dz. Now dx dy dz is the volume of the element. It represents volume of element. Therefore, the total flux flowing out per unit volume, total flux flowing out per unit volume is divergence of the vector point function, and that divergence of the vector point function is dava vx by dava x plus dava vy by dava y plus dava vz by dava z. Hence, total flux flowing out per unit volume represent divergence of a vector point function. That term is a scalar term. Hence, this term we simplify under the physical significance of divergence of vector point function. Now, we suppose if we considering we choose a flow of fluid in case of flow of fluid, means we choose a point in the fluid and suppose divergence of the vector point function is positive. At which point? A point in a fluid. Then what it suggests here? The fluid is expanding. Fluid is expanding from that point and its density decreases with time. Therefore, that point we call as a source of fluid. In other case, if divergence of the vector point function is negative at a point in a fluid, then at that point fluid is contracting. Fluid is contracting. And if fluid is contracting, then what happens about its density? Its density increases with time. Therefore, at that point, it acts as a sink. In other case, if divergence of vector point function is 0, means what happens? The fluid does not expand or contract. Fluid becomes compressible means density of the fluid remains constant. That means the vector at that point becomes a solenoidal vector. Hence, when the vector becomes a solenoidal vector, when a point in a fluid, at that point the fluid does not expand or contract, it becomes incompressible and its density remains constant, means del dot V is 0. In such a case, the vector point function which acts as a solenoidal vector, and that is the total term under the divergence of a vector field. Hence, divergence of a vector field, we prove it is a scalar quantity. Under physical significance, we prove that the total flux flowing out or diverging per unit volume of volume element in the vector field region along x, y, z axis. For that purpose, firstly we calculate what is the magnitude of the vector along x axis if the flow is taken along positive x direction as well as negative. Then the magnitude of the velocity, magnitude of the vector if the flux is flowing in into the element as well as out through the element. And if vector v and normal drawn to face area of the element are in the same direction, then flux is taken to be positive, otherwise it is negative. Hence, using the flux flowing through any face of the element, we calculate along x, y, z axis. Therefore, the net flux flowing, total flux flowing out from the element is dA by Vx by dA by x plus dA by Vy by dA by y plus dA by Vz by dA by z dx dy dz. Hence, total flux flowing out per unit volume is a scalar term, and that is dA by Vx by dA by x plus dA by Vy by dA by y plus dA by Vz by dA by z. Thank you.